particle technologies team, which I run, and the reactive chemistry team, which is run by the founder of the company. And we have ONTO, which is a highly reactive surface modification chemistry, but most of my time is spent worrying about anti-reflective coatings for displays and ophthalmics. So it's one of those companies where we do quite a lot of work on the base materials, but then we go into all sorts of different industries. And one of the challenges there, of course, is it's very easy to kind of blunder naively into a new industry without really understanding it. And that's one of the things that when a new project comes in, I'm always very cautious about, which is where METRC came in. So, as I say, the ONTO reactive chemistry is an organic chemistry technique based around highly reactive carbines, which has been developed by Mark Maloney at Oxford over the last 10 years. And they're so reactive essentially, once they're activated by heat or UV, they react with whatever they're coated onto the surface. So we do a lot of work with polymers, making them hydrophobic, that kind of thing. And also, I come from a background of nanomaterials, so I'm interested in making thin films. So with the anti-reflective coating, we're then working on particles, not just on the synthesis and the properties of particles, but also on the surface modification and the deposition of particles. So, I guess about 2 years ago, we were approached by a large global agrochemical company whose name I can't tell you, but doesn't begin with S, okay? Because everybody always says that. And they came to us and they said, well, okay, we've got an interesting challenge here. You like modifying particles and handling particles. Have you ever thought about modifying things like herbicides? I said, no, I have no idea, I don't know anything about herbicides. I'm usually stripping oxides, actually, truth be told. But they said, well, there's a real issue with herbicides as they're sprayed onto the ground, in that actually about 90% of it doesn't end up in the plant, which is what you want it to be. You get runoff, it goes through into the water table, you get degradation, you get spray drift, which is as the wind comes across and takes the agrochem away, and there's all sorts of different structures in soil. Soil is a highly complex system, as you might imagine, and there's a real issue here. And also, the thing that actually really attracted us is if we have a look at what the market is, it's actually huge. So you've got 1 million tonnes of herbicide being sprayed on crops, and 90% of that isn't going into the crops. That's basically environmental contamination. And these things are toxic. I mean, they're herbicides, they're obviously toxic in high concentrations. It's a growing market, it's a high value market. And again, most of it isn't actually getting to the crop. So, obviously, I was kind of interested in this because, you know, there's an obvious market, there's an obvious market need there. The first thing I thought was, well, I don't know anything about soil, and I don't really know anything about colloidal flow, that's not really my bag. So I went on to Science Direct and downloaded a few papers on soil chemistry, and read them, and then went for a long lie down in a darkened room thinking, oh my God, this is a really complicated system, I'm not really sure we should be getting involved in this at all. And then happened to bump into Simon at a conference in London. I can't remember what the conference was, but I remember bumping into Simon. And I said, well, we've got this company. Do you have anybody in the METRC group that knows anything about soil? Even in the first instance, I can just say, am I completely barking on the wrong tree with these ideas? Because I was thinking about maybe having a silicate column where we could run materials through and see how they stuck and how they went through, and then maybe going into soil, and then I guess our customers would want to do greenhouse trials and that kind of thing. And Simon came back and said, well, actually, there's Professor Stephen Badward and his team, of which Maria's part, up in the university, were doing an awful lot of work on transport of colloids through soils. And I actually thought that name rings a bell, because that's one of the papers that I downloaded and actually had a look at where the material went through. So that's how the collaboration started. Of course, it was tremendously valuable because I didn't really want to go back to the company that were paying us and start to say, I had these ideas, are they completely wrong? Because that would make me look like a bit of a chump. So it was really good to have a collaborating team that I could actually bounce ideas off and actually start to develop our own assays in-house. So I'll tell you a little bit about how it all works. Well, we were approached. I can coat particles, I'm fairly happy handling particles, but what I don't know is I have no idea really about agrochem or soil transport materials or anything like that. And that's where the guys in Sheffield came in. So we put this all together under under the METRC, and we kept these guys informed, but they weren't directly involved in the proposal. They were kind of interested in what was happening, and actually their view was, well, if it helps us get to where we want to go, then that's a good thing. So the idea was that we would do a fairly simple coat of the herbicide. We would do some simple assays. We would just take a column full of silicon materials and choose the materials that we thought worked best in these simple quartz assays, and then they would be run again as quartz assays, but also as soil assays and initial greenhouse trials in Sheffield. So there is quite a technical challenge here, in that the first thing that's got to happen when you've got a soil particle, known as the collector, well, first of all, you've got to choose which one it's going to be. So we chose silicates. You usually have silicates, iron oxide, and organics, depending on the soil type. First thing that must happen is the herbicide particle actually hit the soil particle. And there is an awful lot of maths behind here, which I didn't really think you'd be into particularly. But the bottom line is there are about 7 or 8 different variables that influence the collector efficiency. But you don't really have any control over them. Because you can't control the soil, you can't control the rate of water flow through the soil because that's just the rain. You can't really control much to do with Van der Waals forces because they don't really make a great deal of difference. The thing you can control is particle size, but actually you don't really want to, because if you make particle size smaller, the material's going, you're changing the almost like the rate of delivery, which you don't really want to change, and you don't want to make it bigger because it's set on the surface. As it turns out, most herbicides, when they're supplied, are exactly the right size to go merrily through the soil without actually hitting the collector very often. So you actually, almost with a herbicide, designed it to go through the soil into the water table. However, there isn't a great deal you can do about that. So what we essentially do is start to look at the surface and modifying the surface so at least when it hits, it's got a better chance of sticking there. And then we'll design the surface such that even though we've got a coating on it, that coating slowly will dissolve away to allow the herbicide to release. So that was the concept. The next thing to do is worry about whether it sticks or not. So the total energy of interaction is given here by these 4 terms. But actually, the reality is, it's that one you want. Because this one, if you get that, the electrostatic charges right, dwarfs the other terms in the system. So, essentially, we know that quartz has a surface charge, a potential, of minus 25 millivolts. And so we measured the herbicide. The herbicide's about minus 90 millivolts. So you've got a repulsive force. And not only have we designed it such that it's very unlikely to actually hit anything as it goes through the soil, even if it does, they repel each other, which doesn't help, obviously. So we used a series of polymer systems that we modified using our own chemistry, which, like the last week, I can't say too much about because I haven't got around to writing patents on it yet. And then we have a water-soluble component in there. So we have the electrostatic attraction when it hits, and then a slow water-soluble component to allow it out. And this is as far as we got. We've got a whole series of different modifications here. And these are all coming through our silicon column assay. So we basically chose the ones down here. So the commercial formulation, what you're seeing here is percent of the herbicide basically eluting at the bottom of the column. So your herbicide, which is the commercial formulation, comes out and starts eluting out down here. So anything this side is sticking better in the column, anything up this side is sticking worse. But you can correlate this to surface charges and things like that quite nicely. So we did, or rather Sergio in our company did an awful lot of quartz assays that have probably scarred him for life actually, spent most of the last 18 months doing quartz assays until we were happy that we were getting reproducible data. And then essentially we chose this one down here and so that's as far as we can go. And then we handed it over to the guys at Sheffield to do further work there on soil and on some initial greenhouse assays.
Just, yeah. Right, so what do we do in Sheffield? This is the Environmental Engineering Science team at the University of Sheffield. We're based at the Croton Research Institute. This is in Rock Lane, what used to be the Health and Safety Laboratories. And things we're more interested on are basically looking into processes at fundamental, molecular, and even sometimes atomic scale, understand how they work, and in principle looking into pollutants in the environmental area. And then from there, start constructing or building up blocks to understand how these pollutants may move through the environment. Things we do are molecular biology through porostheria, so understanding biofilm interactions with soils. We go a little bit up the scale into looking into how they interact with plants as well. So we have a system of plant, soil, and potentially pollutants. And the main final output is to look into transport and fate of pollutants in the environment and how one can predict these in the million years to come when we're not here. So we got a team of about 20 members at the moment. We got postdocs, experimental officers, and etc. And then we tap as well into a lot of instrumentation that's based at the Croton Research Institute, like electron microscopes that actually belong to the materials engineering department. But because we're sitting there, we can have access to that as well. So what we did then, once we sat down with Gareth and his team, was to think about how can we take then the real system and put it into the most simple way in order to understand how these particles that we're producing were traveling through soil and how efficient they were into either being retained by soil and act as herbicides per se. So what we went for a very, very simple column setup where we can stack columns with any material we wanted to. We did some of the quartz assay that we're doing as well, so we can have matching results. And then we moved into real soils. And we looked into different soil, different compositions, things that would be more likely to be charged to attract the particles, or things that would be more likely to repel the particles. And obviously, the idea was then to try to measure how efficient the soil is in retaining the particles. That was the question they wanted to know. And how efficient it would be to kill plants eventually. So we did that, look into sort of different setups and etc. And again, we can't give too much information here due to all the protected information we work with. And the basic thing we found out is that OAS were producing formulations that were quite efficient to be retained by soil. They were acting better than traditional commercial products that are out there, and they were staying for longer, and therefore the main aim of trying to have a small rate of herbicide applied into the soil that's going to be more efficient in the long term seemed to be, from only the physical-chemical point of view, being met with the particles they were producing. So bearing this in mind, this was only half of the story. We knew we could then identify the number of particles that were being retained by soil. We knew that the formulations that we're producing were good enough to do this type of work. But were they good enough then to kill plants in the end in a shorter time? So we moved from there into a greenhouse trial. But the METRC funding wasn't really enough to do the greenhouse trial. So due to the success of the collaboration at that point, we applied for a little bit more funding, basically just to fund the part of hiring the greenhouse facilities in Sheffield, like the animal and plant sciences. So we applied for a small fund to the knowledge transfer short project, and then we got a little bit more money to hire basically the greenhouse and do some studies in there. So what we did again, we went for a small type of trial, very simple again, 2 different stream type of soils, 2 watering this in different regions. And when we use some plant species that are widely used to test these type of products, and we use 1 plant control as well. And in this case, Gareth and his team produced 5 different herbicides that we contaminated these plants with, and then we went looking into what happens to the plants in the end. And this is the type of typical results that I love from this very simple setup. Plant is alive, plant is dead. The product works, basically. And that's what we wanted, isn't it? All we wanted was the demonstration that it works. But more importantly, from these trials, what we wanted to know was whether it would be more efficient than commercial product supply to it. And, this is, instead of reading this, I'll just leave this one, which is nicer. So what happened in the end is that once we use some of the formulations produced by Gareth and his team, compared to the commercial formulation, what we found out was that the plants were dying faster in a shorter time than the plants that were exposed to the commercial formulation. And this is good, because what we wanted was that they were in the soil, they could act fast, and they were not moving too quickly. So whether any more wheat was going to be growing in that soil could be killed in the long term as well with these type of compounds. And it does work. So we can't give you more information because, as you probably guessed by now, we want this to create lots of revenue in the end. So it works quite well, it works in a short time, and it probably will be, as far as we want to know, very environmentally friendly. So what we want to do now, because we still got more work to do, some of the trials that we want to develop, is to do some dose response experiments against the commercial standards, of course. And we need to be filing some patents as well. Like I said before, METRC funded the first part of the project, and then we needed a tiny little bit, it wasn't much, to hire the greenhouse. And obviously, because we demonstrated we were getting very good results, then we got that bit of money as well. And therefore, we want to apply for a bit more money in the end after this project finished last year. One thing I wanted to highlight as well was why this collaboration worked. We didn't know each other. It all happened because Simon and METRC were there, and people go looking for people around there. But why this collaboration worked is because we worked together from the beginning and still working together very, very closely. One of the things that I found very helpful from this collaboration is the fact that these guys were coming down to Sheffield every 4 to 6 weeks. We had very, very close meetings. I had the staff we had through METRC in Sheffield working in Oxford. The staff in Oxford came and worked in our laboratories in Sheffield. And the fact that we kept all this relationship very close and all the time checking on what each other were doing and how to drive the project forward in a better way allowed us then in a very short time, with the amount of money we had, to get good results. So we're going to keep doing it, aren't we?
I hope so, yes.
Right. Thank you very much for listening, and I'll take any more. We'll take any questions as well.